It's kind of funny. Every time I give a talk in this space, it just keeps filling and filling. And I wonder what the theoretical limit of the space here. Maybe we'll learn in like half a year or a year, right? Like filled to the room and stuff. Anyway, hi. Thanks for coming here. My name is Trent, and I'm one of the co-founders of BigChainDB and Ocean. And tonight, I'm going to talk to you about sort of a slice of topics related to things we've come across as we've been designing Ocean. And it's going to draw on my experience over the last couple decades with the world of AI and optimization. And you will see what I mean as I get into the talk. So without further ado, let's get started. So the title of my talk is Token Design as Optimization Design. And well, I'm not even going to unpack those right now. I will unpack them as we go. But a bit of an outline, I'm going to talk about how you frame blockchains maybe in the past as trust machines, also as incentive machines. There's a sort of a new way to think about it that's actually super powerful. Then I'm going to give a bit of a case study on Bitcoin just to sort of set the stage. And then talk about how we can start moving towards a token design practice from things we're observing out there, the case study of Bitcoin, what other fields have in terms of thoughts for this. And then I'll use that as sort of how we're thinking about Ocean. And then finally, just sort of underscoring why getting the objective function right really matters. And objective function as in BlockReward Function. You'll hear a lot more about that. So let's get started. Some of you, there's probably many new faces here and some older ones, but to give you some of you guys a bit of a learning, I'm going to give a couple slides, sort of with the basics of blockchain, right? And by the way, I heard recently, if you're in a room where you ask 4 blockchain experts for a definition, you'll get at least 4 definitions of blockchain. So, myself, I'm going to right now give you at least 4 definitions myself of blockchain, starting with the very basic and then building up to some fancier ones. So a blockchain data structure is simply a chain of blocks, right? What's a block? It's simply a list of transactions, where inside a transaction you can create an asset. It might be a Bitcoin asset, might be digital art, whatever. And the other action is to transfer that asset. So 2 main actions, issue an asset, create it, and then transfer it. And each transaction, crucially, is digitally signed. It's sort of like applying your password or your private key to that transaction so that it's known that only you did it, right? So that's the block part, this list of transactions, right? The chain is simply linking these blocks together, right? A chain is simply a linked list of transactions. And those of you who have spent time in computer science, linked lists are not new. They've been around a long, long time. Traditionally, linked lists are in memory. So you have pointer to the previous block in memory. In the case of the blockchain world, it's hashes. And that gives some special properties, basically sort of like, it makes it more and more immutable. It's sort of like rings in a tree, one link on top of another link on top of another link. So it makes it harder to undo, as we'll see later. So that's really one definition, is the very most mundane definition of blockchain, simply a chain of blocks, a linked list. You can also, though, think about them as a distributed database, right? So, databases have been around since the 60s and 70s. Initially, they were called AI until, it was no longer magical, so they started to call them something that was a little less crazy sounding. And basically, they call databases with things like SQL querying and all that, right? So the very essence of a database really is about querying. You have a bunch of data that you're storing, and you want to be able to access it quickly, right? And you can have SQL queries, which you sort of have a table, or you can have these NoSQL databases, which generally have better scale. So what we had actually in the late 90s and early 2000s, the web started taking off. So people started making these things called distributed databases. Up until that time, when people had a database, they'd have just one big box storing a bunch of data. But then, web was blowing up. So people said, what if we had 10 boxes or 100 boxes or 10,000 boxes? But it felt like one box, right? So you query that one box, there's one sysadmin for that box, but you have 10,000 machines under the hood. That's a distributed database. That's what Google and Amazon and Facebook run. This is what MongoDB is, all these things, right? So these things have been around a long time, distributed databases. Lots of machines, one sysadmin, right? So you can think of a blockchain as a distributed database, like MongoDB, but it has 3 new characteristics, right? It's decentralized, so instead of having one sysadmin, you have 10 or 10,000 sysadmins, right? And generally for that, you want to have some sort of consensus that's fault tolerant, Byzantine fault tolerant, etc. So that means if one of the sysadmins goes in and starts, kicking it badly, the whole thing doesn't fall on its face, right? You want it to be immutable, so that means if you want to undo a transaction, so once something is in there, you don't want to make it. You want to make it really hard for other people to undo that, right? So if I send Bitcoin to you, it should be really, really hard for someone else to undo that, or really hard even for me to undo that, right? And finally, the idea of assets, the idea that I could issue assets. I can issue bitcoins or digital art or whatever I want, or digital twins, like Karsten was talking about. I'm a twin, so I like the idea of analog twins still. Thank you very much, but digital is good too. And I give the example here. BigchainDB is a very good example of a blockchain database. It starts with a database. It actually wraps MongoDB and adds in these characteristics on top. And we designed it to basically take advantage of all the innovations that the MongoDB team had done over the years, and built on all the innovations of the distributed systems world over the decades, and then adding these new characteristics. So now there's another characteristic you can think about, and that is going from permissioned to permissionless. And this really comes down to who is allowed to validate whether a transaction goes through or not, right? So in permissions, to be a server node, to validate whether a transaction goes through, you need to be on some pre-approved list, right? It can be, this list of sysadmins. So you've all got together and said, okay, here's the 10 public keys, the 10 identities that are okay, right? So it comes down to basically one public key equals one vote. That's really the idea of a permissioned setting, right? You can call these consortiums, you can call them federations, all of that, right? By the way, that's what BigchainDB is well suited to right now, right? There's also this idea of permissionless, right, or public. And this means anyone can join as a server node, right? And to do this, you not only need tolerance to the Byzantine faults, the malicious attacks, you also need Sybil tolerance, or attack of the clones. And what that means is, you don't want it where I come in and make 10,000 copies of myself and then get 10,000 extra votes and swamp it all, right? So the Bitcoin approach to that, to solve that, is saying, okay, instead of having one public key equals one vote, it's one electron, one vote, right? It's a perfect democracy for electrons, right? And what this comes down to basically is, if I spend lots and lots of electricity for lots and lots of hash power, and then maybe I have 10% of the hash power for the network, so I roughly get 10% of the vote, right? That's kind of how Bitcoin works. So that's one approach to Sybil tolerance. In general, you just need some way to address this attack of the clone problems, right? There's other stuff out there coming out, things like proof of stake, etc. I won't get into that, but I just want to emphasize this distinction of permissioned and permissionless, right? Both have their uses, both have their use cases. It really depends what you're aiming for. And of course, the beginning of this section, I talked about blockchains as trust machines, right? And there was an article in The Economist, cover article 2 years ago, where it talked about the trust machine, right? How the technology behind Bitcoin could change the world. And this was even before the banks got into it and so on. And it uses the word trust because it's this idea of minimizing trust needed to operate, right? So before, if you want to use a bank and so on, you're actually paying the bank a lot of money in order to trust that bank, right? They have this long history, they're big, all of this, right? Whereas the idea of blockchains are you actually can get a similar level of trust without actually needing to pay a bunch of people a bunch of money and hope that they're going to be trustworthy, right? So in the words of Nick Szabos, who, some people say is Satoshi, who knows, blockchains, public blockchains especially, are more socially scalable, right? So you might even trade off a lot in terms of compute efficiency or electricity in return for this social scalability, right? So that is blockchains as trust machines. But, they're not just that, right? There's actually more to blockchains, and they can do some extra interesting things. So I've talked so far about how blockchains, above and beyond distributed databases, for example, are really nice for decentralization, immutability, assets, but there's one more thing. And I actually have to admit, I kick myself for not really fully getting this until, say, the last year and a half. But, I'm happy to have learned, and I want to share, that with you. Maybe most of you already got it. Maybe I'm a slow learner, but let me tell you, this is the blockchain superpower. Blockchains are a way to get people to do stuff. How? You pay them magic internet money. You reward them with tokens, block rewards. If there's one slide you remember from my whole talk tonight, this is the slide. Blockchains are a way to get people to do stuff, okay? They are incentive machines, okay? And once again, how you get them to do that stuff? With tokens. Right? So I'm going to drill into what this means, and then the theory around how to think about this and how to design for this, right? So the power of incentives, right? So Charlie Munger, he is the right-hand man of Warren Buffett, very, very successful as an investor. To quote him, I think I've been in the top 5% of my age cohort all my life understanding the power of incentives, and all my life I've underestimated it. So all his life, he's actually been using incentives, understanding, and at the same time he continually realizes, wow, they're even more powerful than I realized, right? Never a year passes that I don't get some surprise that pushes my limit a little farther, right? So if you think, yeah, Trent, incentives are kind of cool, but maybe not so cool, Don't ask me. Ask Charlie Munger, right? Or defer to some other authority, or ask yourself. And just, you know, watch the rest of my talk, and you'll see some of the power, right? So let's use Bitcoin as a case study of economic incentives, okay? So Bitcoin itself, it came on the heels of the financial crisis, right? And even if you read the abstract of the Bitcoin white paper, you will see the references to the financial crisis and so on, and how there is a need for a sort of a new financial infrastructure for the planet, right? And so the very, very core of Bitcoin is actually about having this list of transactions that is super, super secure, that is more trustworthy than banks or central banks or governments, right? That's really the core. So Bitcoin's goal is essentially to maximize the security of its network. And its network itself is storing this list of financial transactions, right? So it's a financial infrastructure. Now, Bitcoin itself, it actually defines security as compute power. It's actually hash rate, but if you assume that the top miners all have the fanciest modern ASICs, then it's essentially compute power. So therefore, you make it super expensive to roll back the changes to the transaction log, right? So the more security you have, the harder it is to undo those transactions. So if you've got the rings in a tree, even to undo one ring will take a lot. And to undo a second ring will take a lot more, and a third ring, and so on, right? So try to do, you know, 10 rings back, which is, you know, 10 times 10 minutes. And that's already super, super hard, right? And this is why we don't see unrolling of the Bitcoin network, simply because it's just so hard, right? So this is Bitcoin's economic incentive. This is what it's aiming for, right? Now you might ask, okay, well, how does Bitcoin manifest this, right? Well, it turns out, at the very core of it, it's got a block rewards function, right? An objective function in optimization parlance. What is it? It's the following. I only have a few equations, and they're not that scary, so please bear with me. So basically, the expected reward, the expected number of tokens, i.e. Bitcoin, coming from the Bitcoin network for any given time interval, you know, in this case 10 minutes, is proportional to the hash power of that actor compared to the rest. So it's, if I have 10% of the hash power at that time interval, then I have a, and right now there is 12.5 Bitcoins every 10 minutes coming out, then I can expect on average 12.5 times 10%, or 1.25 Bitcoins every 10 minutes. Now, of course, the way that Bitcoin works, it's a winner take all any 10 minutes, right? So it might be only 1 in 10 times that I win, but on average, my expected return is that, right? It's my hash power compared to my number of tokens. So I could even take my laptop right now, start running out on the Bitcoin network, and I might have like a 1 in a million or 1 in a billion chance of actually getting something, but I do have a chance, right? Now, what this means, so we've got this expected value, right? But it's very lumpy. There's very high variance because it's only one person takes all. It could have been set up where, you know, for everyone who contributes hash power every 10 minutes, they get back their tiny, you know, small amount of Satoshis. But for efficiency and security reasons, almost certainly, this is why Satoshi did it, where he said, or they said, you get just one winner, right? Because then it's just one transaction every 10 minutes going to the winner, right? Now, if you want to smooth out the variance, if you want to make it more evenly distributed, you can. How? Mining pools, right? We have this emergence on top of Bitcoin of mining pools. So if you have a laptop and you want to make, you know, 100 Satoshis every hour, you just join a mining pool and then you'll get, you know, your Satoshis in proportion to how much mining power you have to contribute. But it all comes down to this. This is the BlockReward function for Bitcoin, the optimization function. And it is working directly with the goal of maximizing the security of Bitcoin. This is Satoshi's goal, maximize the security of the Bitcoin network, right? And everything else that we see in the Bitcoin ecosystem emerges from that singular objective function. That's really the key thing to remember. You know, a couple more details here. There's the Bitcoin token release schedule, right? Which is over time, there's a number of Bitcoins that came out. So the way that Bitcoin works, you know, when Bitcoin first came out, the network in early 2009, there was 50 Bitcoins every 10 minutes. And then every 4 years, in Bitcoin's case, there's a halvening. So after 4 years, there was 25 Bitcoins. And then after 4 years more, there was another, it was divided by 2 again. So that means every 10 minutes now, there's 12.5 Bitcoins. It also means that more than 75% of Bitcoins have already been given out to people, right? And it's going to diminish over time. And this time scale here, it works out to over 100 years, I think 140 years, before basically all Bitcoins are out there, right? So basically, this is just happens to be the token reward schedule. And this plays into the T here, right? So there's lots of other potential token reward schedules. This is just how Bitcoin does it, right? So this was the Bitcoin objective function. You might ask, well, how successful was it, right? Well, actually, let's start with this. This is actually the hash rate, the growth in the hash rate of Bitcoin. So it's optimizing this objective function. And this is actually just since July of 2015, so up to May of 2017, so roughly 2 years. And we can see in this case even, it's went up by a factor of 500,000 to 5 million, so 10x, right? And if you actually stretch it over the whole time scale, it's actually exponential growth, right? So this shows that Bitcoin, the network, is doing a great job in maximizing its objective function, which is maximizing the hash rate, i.e. the security of Bitcoin, right? And what do we have in the end? Well, we have the massive mining pools like we've talked about, as well as we have things like this. This is a data center where every single one of these is a computer with a whole bunch of ASIC chips. And these ASIC chips, computer chips, they're actually manufactured in the most modern of processes, 11 nanometers. To even manufacture one spin of that costs $50 to $100 million. You really, really have to be dedicated, right? So we have companies out there now that actually they spend $50 million, $100, $200 million to design and manufacture these chips. They put them into these massive ASIC farms and they do that. And guess what? Bitcoin never told them. It all comes down to the power of this objective function, right? This BlockReward function. All these people are working in service of this thing called Bitcoin that is paying them in magic internet money to build these. Isn't that remarkable? So you might ask, okay, that's Bitcoin, right? And by the way, there's a lot of other examples out there too, and I'll give some examples for Ocean later. But with this, in designing Ocean, we were asking, okay, what can we look out there to learn about this, and what is going on under the hood? And I hope so far I've started to give you some intuition, what the most important thing is here. But then from that, how do we actually implement, how do we take these ideas and learnings and other learnings from other fields towards a design practice for tokens? Ultimately, I would love to see, just like we have software engineering and electrical engineering, I want to see token engineering or incentive engineering, right? But we're not there yet. Right now, it is the Wild West in terms of design. We are flying by the seat of our pants. So I've been struggling to try to figure out, along with my team at Ocean and colleagues throughout the world and friends, to try to wrestle this thing down and try to put a bit of theory onto it. So the next few slides, I'm going to talk to you about a related field called optimization. And optimization actually goes back to the 50s and before, where people have been doing everything from maximizing the efficiency of a car for its miles per gallon to minimizing the time that it takes to fly from Earth to Mars, right? So or minimizing the power of an electrical circuit, right? So this is the field of optimization. We have everything from gradient descent methods, which climb up a hill, to global optimization methods, and even subsets of AI like evolutionary algorithms, right? Where it's, you've got this sort of survival of the fittest happening, a population of individuals trying to get to that optimal design, the survival of the fittest design, right? So that's the idea of optimization. And there's a few steps that you take when you're doing optimization. And by the way, so my very first company, this is what we built. We actually built an optimizer for electrical engineers, analog designers in particular. So if you were designing an op-amp or anything like that, my company was actually building the leading tool in the world for that. And it started in '99, sold in 2004. It was widely used in the industry. So I played with optimizers a lot. I've talked the ear off many people about optimization over the years. I'm only going to talk your ear off for 2 or 3 minutes about this, and then we'll move on. But there's a few steps, okay? So step one is you need to formulate the problem. You need to describe the problem in mathematical terms, okay? So just like you saw before, I formulated the problem for Bitcoin, saying this is what Bitcoin is trying to maximize, which is essentially the hash rate, right? Well, in the case of an optimization problem, it could be whatever. What is it that you're trying to maximize or minimize? That is the objective function. And in fact, you might have more than one. You might say, okay, I'm going to try to minimize the power of this electrical circuit and maximize the gain bandwidth, okay? Or let's say you're a car designer. You might be trying to minimize the fuel consumption and maximize the top speed, right? And so the more objectives you have, the more things you're trading off. So a lot of things you're just optimizing for one thing. When you're training a neural network, you're generally minimizing the training error, okay? So this is what you do. This is actually from a paper that I wrote about 10 years ago. And in this case, this is saying, it's saying find the maximum value of f of d. And in this case, f of d is the yield of a semiconductor circuit, a chip basically, right? And then it goes along and describes the design space, like you can wiggle these variables like this and these variables like that. And then, and this f actually expands through the y, and then the y expands to this fancier integral here, okay? But that's just the objective function. Besides that, though, you have constraints. You have things that you need to meet. You need to be maybe saying my power consumption has to be less than 10 milliwatts, or my top speed has to be greater than 60 miles per hour, because otherwise everyone will hate you on the highway, right? Et cetera, et cetera. So there are constraints, inequality constraints, equality constraints. And this is just a classic practice, if you're a professional at all in the world of optimization or a related field, the first thing you're going to do is going to write this down in terms of equations, right? And the classic formulation is the following. You've got one objective or many that you want to minimize or maximize. See, I have 1 to NF. Then you have subject to inequality constraints, right? Things like top speed must be greater than 60 miles per hour. And equality constraints. Things like maybe you need to say, no matter what, I need 40 miles per gallon, right? Not higher, not lower, I'm just equality, right? And then this is within the design space, right? So maybe saying within the space of all aluminum bodied cars. You're just going to say straight out, right? Not even in beyond that. And so this is just the classic thing. You want to formulate objectives, inequality, and equality constraints. Okay, I don't want to bore you guys too much, but the next step then is once you have that problem formulation, what you then do is you look around to see, are there any off-the-shelf algorithms that I can use, right? Are there, maybe this is just a local optimization problem. I'm okay to just run up a hill. Or maybe there is just one big hill. Or maybe there's a whole bunch of hills, and I can't get stuck on one hill, so I need to try different hills. And so if it's just a local optimization problem, I can use a gradient descent, like a Newton method or something. But if I don't want to get stuck, then I have to use something like a global optimizer. And even with those, there's ones that guarantee you get to the top, and there's other ones that you kind of hope and pray you get to the top, right? And then, sometimes though, there's not even, for your problem, there's not even anything out there you can use. And then you have to invent your own, right? And, this is the world of PhDs, right? So how I got part of my PhD was inventing some new optimization algorithms back in the day, because, then I could publish and solve some new problems and so on, right? So this is some algorithm that I published also like 10 years ago. And it looks kind of cool and all this. And it doesn't look any different than other computer science papers, right? If you read papers in the consensus field or in other fields of computer science or engineering, you'll see things specified this way. This is just a specification of how an algorithm works. It's pseudocode, right? And then once you've got that optimizer chosen or designed, you run it, right? You see how it's converging. So in this case, I was running an evolutionary algorithm. And its time scale is in terms of generations. So it runs 100, 200, 300, up to 500 generations. And in this case, it's trying to minimize some error function, right? And you can see the very, very best is this. So it comes along here. And after 200 generations, it's essentially got 0. But there's other ones running along, and they're not doing so well, right? They're getting stuck here. See, this one got stuck. So I have many, many runs here. And one of them did really well. Some other ones did so-so, right? And so what you do, if you've done a good job designing your optimizer, then you've actually, converged. And if you haven't, then you have to go back to the drawing table and try again, right? So why I describe this all to you is simply, this is a practice that has actually been around for decades, right? For designing optimization problems. This is actually how modern cars get designed. This is how modern computer chips get designed. All these sorts of things, right? And this can help point towards a practice of how token ecosystems can get designed too. So I'm going to start leading to that now, and I'm going to use the example of evolutionary algorithms in particular. They're special. They're actually closest to token design simply because of a few characteristics. So this slide here is basically showing a very direct comparison of how optimization design is super, super similar to token design. So first of all, we have the goals, right? Which is the objectives and the constraints I give here. I just say objective function. So in the tokenized ecosystem, we've got the BlockReward function, right? So maximize hash rate, like Bitcoin has, right? Or in an evolutionary algorithm, which is a very particular type of optimizer, survival of the fittest, basically. Minimize error, right? So maybe you're trying to use an evolutionary algorithm to train a neural network, right? And that's common, so you could do that. And then, how do you measure it, right? How do you know whether this thing is working or not, right? In the world of evolutionary algorithms, it's whatever you're optimizing for. You might simulate an electrical circuit, something like SPICE, which is a dynamical system simulator. And crucially, in the world of blockchains, this is a proof. It's a computational proof. And so in the case of Bitcoin, if you actually find that block reward, you're solving this cryptographic puzzle, right? You're trying to find this nonce that can find this particular hash that Bitcoin is aiming for, right? And if you find that, then you submit that to the network, and you get your 12.5 Bitcoins, right? And it's essentially proven that you've actually, solved it. And that's essentially evaluating an objective function in the world of tokens, right? And there isn't just this, Bitcoin variant of proof of work. There's other sort of human proof of work, like Steemit has. There's proof of stake in various ways. Or like, for example, Augur, which is a prediction market. You want to prove that maybe people are predicting that it's going to rain tomorrow, right? And there's people predicting, yes, it's going to rain, and people that they're predicting it's not going to rain. And so people bet on one versus the other. And then tomorrow, to actually know what happened, Augur assumes that the majority of people will, when they report what actually happened, the majority will report the truth. And they're incentivized to report the truth in this sort of Schelling point. So it's sort of convergence to the truth. And then basically, once that truth is reported, then people get paid out. So in the case of Augur, it's actually using some human psychology towards the Schelling point. So there's a lot of different cryptographic proofs out there. Proof of space-time for storage. There's lots of proofs for computation too, like zero-knowledge proofs, et cetera, right? So this is a really, really big subset. And my colleague Dimi was actually going to talk tonight to really zoom in on that. He's sick, so I guess he'll be talking about it another time. But this thing here is the talk of like, is the content of not just one talk, but another 50 PhD thesis. And we're seeing this now, right? Keeping going, so on this comparison, right? So we've got the goals, the objectives and constraints, and we've got the way to measure, right? But there's a bunch of other things that are really interesting too. So in an evolutionary algorithm, it's survival of the fittest, right? So these individuals, they run around, they do whatever they want, right? But at the end of the day, they get evaluated against this objective function. So you don't really care what they do until you evaluate them, right? They mutate, they cross over, it doesn't matter, right? And in the case of tokenized ecosystems, you've got miners, token holders, they're all running around doing whatever they want. Bitcoin don't care, right? Honey Badger don't care, all this, right? It really doesn't. All it really cares about is, give me that nonce, solve my problem towards optimizing this objective function, right? Everything else, it doesn't care. So it's very, very similar to evolutionary algorithms. This is a difference compared to other algorithms, optimizer algorithms, where they might, for example, compute the gradient. So it's sort of like a top-down saying, go here, then go here, then go here. Evolutionary algorithms just say, do whatever you want, right? And it's not just evolutionary algorithms. There's this whole class of optimizers called swarm optimizers or distributed agents, these sorts of things. So all these sorts of algorithms do that. Then there's actually a system clock, right? So in blockchain land, we've got the block reward interval. In the case of Bitcoin, it's 10 minutes. And in the case of evolutionary algorithms, it's called a generation, right? Interestingly, there's a continuous variant of each. So you could actually just continuously give block rewards over time if you wanted. And in evolutionary algorithms, it's called a steady state evolutionary algorithm. But it's usually conceptually easier to think about blocks. And finally, in terms of incentives and disincentives, right? How do you reward these things for doing well or not, right? So in the case of evolutionary algorithms, basically if they do well, you let them have babies, right? And mutate and cross over and so on. Or maybe if they do badly, you kill them off. And in fact, you can have an evolutionary algorithm that converges simply by killing the worst 5%, and that's it. And over time, it will converge. Well, similar thing with blockchains, right? With tokenized ecosystems. So you can't control the humans or the agents running around. I mean, there could be AI agents here, right? All you're doing is rewarding them in tokens if they do what you want them to. Or if you want, you can also simply slash their stake. And this is an emerging practice, right? And this is also a wildly powerful idea on its own. So to summarize, there is, evolutionary algorithms go back to the 60s. So 50 years with a body of literature on that. There's probably 5,000, 15,000 people in that field. All those ideas, oh, there we go. All those ideas, there's a ghost in the machine too, I guess, right? So all those ideas, we can start to apply to tokenized ecosystem design, right? And by the way, it's not just optimization. It's not just evolutionary algorithms. There's a broader way to think about this. So if you followed blockchain at all, lots of people like to use the word game theory. And this is sort of a branch of economics and computer science. It's sort of a mix. And that's really the analysis side of things, right? So people taking game theory to analyze things. But there's sort of a synthesis side of things where you're designing something, and that's actually called mechanism design, right? And just watch, in the next half year and the next year, you're going to see this word a lot more, right? Why? Because this is actually probably the best field to describe what's going on, and it also has its own long history. The challenge is the people in that field are mostly economists and theorists who haven't been deploying systems, because if you design an economy, where do you deploy that economy, right? So whereas, actually, if you take mechanism design and you apply just a few constraints towards making it a bit more practical, you actually end up with optimization design, right? And the good thing about optimization design is people have been deploying this to practical systems for 50 years. This is why we can actually leverage a ton of ideas from here to apply to really what's actually called mechanism design. And actually, there's other labels for this too. So I talked about mechanism design, right? People like to use the label of tokenomics. It's kind of cool sounding. Or cryptoeconomics. Actually, in the late 90s, the cypherpunks back then were calling it financial cryptography. I also actually like token engineering, and I especially like incentive engineering. Why? Because ultimately, I want to end up with a practice, a field, just like electrical engineering, just like mechanical, and I want it to be about incentives. Tokens are a piece of that. Stake is a piece of that. Crypto is a piece of that. But at the end of the day, it's about incentives. So this is kind of my dream of seeing the field ending up here. But this field actually is a combination of a ton of other fields, right? So back in the 50s, there was a field called cybernetics, right? Norbert Wiener invented it and started to write about it. And he became kind of unpopular for reasons not related to his technical work. And basically, people in the subsequent decades reinvented a whole bunch of his stuff, including chunks of game theory, chunks of optimization, chunks of control system, chunks of electrical engineering. So cybernetics, though, is so broad, it actually covers a lot of these ideas. Economics as well, game theory I've talked about, electrical engineering. I'm trained as an electrical engineer. Half of our training is actually about signals and systems, right? And designing things that manifest signals and systems, right? Whether it's as analog circuits, whether it is digital circuits or otherwise, right? So electrical engineering actually has a lot to say about designing tokenized ecosystems, which at the end of the day are dynamical systems, right? Finance has things to say, computer science has things to say, and obviously these overlap too. Behavioral psychology has a lot to say too. I've talked about optimization. I've mentioned control systems. Complex systems, it's sort of a bit of a generalization of AI or optimization, and its core idea is saying, with a very, very small rule set, if you let things happen, you end up with a lot of emergent complexity, right? And that, if you think about Bitcoin, that's exactly what's happening. It has a tiny, tiny rule at the core, this objective function. And from that, we have all this amazing emergent complexity. So complex systems field has actually a lot to say. They also are leaders in the world on agent-based simulation, which we could really use. So basically, there's a lot of fields that feed into what will be called one of these. This exists, and some of the other ones sort of exist, but we'll see. And maybe they'll all merge into one. Maybe there will be three. Maybe there will be competing camps like we see in other fields, right? You know, no one agrees on the definition of blockchain. No one agrees on the definition of AI. And here, probably no one will agree on what the right word for this all is. We'll see. Also, by the way, you know, so I spent time writing optimizers for circuit design, right? And how do people use these? You know, they're designing these chips with 1 billion transistors, right? How do they possibly design them? They've got a simulator called SPICE or something, which actually simulates the dynamical system of 1 billion transistors. And they've got CAD tools to figure out, okay, if I put this thing, this transistor here, it'll do this. And these 4 transistors have the biggest impact on yield, et cetera, right? How are we designing tokenized ecosystems right now, right? Guess what? By the seat of our pants, right? With some theory, with some equations, talking to some people, there's starting to be inklings of simulators, but it's really, really basic, right? So it's sort of like we're designing these ecosystems the way that we were designing circuits in the early 70s before SPICE existed, right? So what we desperately need in the field, and anyone listening to this or watching this later, please, right? We need simulators, which are essentially agent-based systems for this, whether it comes from the complexity science field or otherwise, and CAD tools for token design. I want to see the relative impact of this choice of this parameter versus this one, right? So we are at the early stages of this field of designing tokenized ecosystems, of token engineering. And we basically still have no tools. That said, we got to move on, right? So we have to make do with what we have, work with equations, analytically, et cetera, and run with that. So with that, I'm going to just talk briefly about Ocean and sort of how we've taken these learnings for designing Ocean protocol. So for a bit of background for you guys, I'll take about 3 or 4 slides to kind of set the stage of what we're trying to do with Ocean. And then I'll take a couple slides to just describe, you know, how we have addressed it. So overall, in the world of AI, right? When I was a researcher in the 90s, my very first job in 97, I was given a data set of 20,000 data points. And I was asked to classify between 13 different classes, right? And at the beginning of the summer, it was a summer job, I had an accuracy of 55%. That meant 45% error, right? And I worked and toiled and played with neural networks and genetic programming and all this. And by the end of that summer, 4 months later, I had managed to improve my accuracy to 65%, so 35% error. And I was actually proud of myself, you know, someone paid me to do AI, all of that. But if you think about it, you know, 35% is terrible. So nothing became of that work, right? I mean, the people that paid me for it couldn't deploy it, et cetera. And guess what? This was actually how most of AI was done in the 90s and before, right? So we were all working off of fixed data sets. And basically, screwing around with algorithms, trying to have a better algorithm. And by the way, it was easier to publish papers in that too, because everyone could compare apples to oranges, right? But a paper in 2001 kind of kicked off this new trend out of Microsoft. And what it said was, instead of simply having a fixed data set, let's have more data. So before we might have had, say, in this case, they had 200,000 data points, and they were comparing 4 algorithms, right? A KNN, a perceptron, and naive Bayes. They're just very simple classifiers, right? And you can see there's anywhere from 75 to 85% accuracy. And you know, people would say, oh wow, you know, I'm 10% more accurate, but it doesn't really matter because you've still got 17% error with the worst. You can't deploy that, right? To deploy an AI in the real world, you need like 5% error, 1%, or even like 0.001%, right? So this is all useless, absolutely, right? The researchers said, you know, Banco and Brill, they said, what if we just add more data? So they added, they went from 200,000 data points to 1 million, to 10 million, to 100, and then to 1 billion data points. And guess what? The accuracy kept going up and up and up and up, all the way up to actually 3% error rate for the best. And notice though, most algorithms, they're about the same, right? And in fact, the simplest algorithm does the best. Now, as an AI researcher, this is a super embarrassing result, right? Because we like to be proud of our fancy new algorithms. Here, it says, you know, the simplest one, an algorithm from the 50s, did the best, right? But this points to something. This is actually the beginning of a huge trend in AI, kicked off largely by this paper in 2001, and then another paper in 2007 by Google called The Unreasonable Effectiveness of Data. And it basically talked about, you know, data is the key, right? Algorithms are important. Data is even more important. And if you have more data, then you can actually solve problems you couldn't solve before. What happened? Well, Google and Facebook and others realized that, okay, let's go and aggressively gather data like crazy, right? Google buys satellite imaging companies for data. Facebook buys data feeds from more than 150 companies. Why? So they have more data and more compute. Then they can actually build better models, have more accuracy, have a higher click-through rate, and basically make more money, right? So, you know, Facebook, for example, they make about $20 per user per year in North America, right? They're pretty happy about that. Why? Because they have really good models of each of you. Great, right? So basically, these companies have realized that data is their moat. They have giant data silos of your personal data, right? And the core of this is AI with its basically centralizing tendencies to build these better models to sell more ads. And so a great summary of this problem from my friend Lawrence Lundy is, the core problem is siloed data with no economic incentive to share, right? You've heard me talk about the silos, and obviously early in the talk, you heard me talk about incentives. So I'm sure you know where I'm headed with this, but I'll drill into it anyway. First of all, let's address the silos. What we need is a new data economy. A data economy that merges the people who have lots of data, and this is every other enterprise except for Google and Facebook, et cetera. Traditionally, they haven't had a lot of great AI expertise because the AI experts are busy off starting their own startups. But these guys start these startups, and they're starving for data, right? So they want data. The enterprises need AI expertise. Imagine if you have an ecosystem that can easily connect them, right? So this comes in the form of a data marketplace. However, if you have just one data marketplace, then you've got another silo. So you need 2 or 3 or 5 or 500 data marketplaces. The challenge with that is, if you have 500 data marketplaces, you have terrible liquidity. Each marketplace is its own tiny silo, and then it's kind of useless. So then you'll end up with a, you know, one winner takes all. But imagine, just imagine, if we have something where there is underlying substrate that actually had all the data for all the marketplaces to access. We have an example of this in the airline industry. If you have ever used Sabre or Expedia or Kayak, you'll go in and you'll do a search for a flight from, say, you know, Berlin to New York, and it will show you the results from a whole bunch of different airlines. What's happened is these airlines have taken their flights for sale, they've put it onto one unified database. It's basically Sabre merged with, I forget the other one, but say Sabre. And so basically it's one underlying substrate of all the data, and then they make that available to all the different marketplaces out there, whether it's Expedia or UnitedAirlines.com or whatever, right? What this means is we have an incredibly good liquidity of the flights that are available, and we have a whole bunch of marketplaces on top. And we actually see innovation in the UX. This is why Trivago looks different than Expedia, looks different than Kayak, right? So we actually, it's very useful for the consumer and so on, right? So Ocean is Sabre for data itself. Okay, so Ocean is designed to let a whole ecosystem of data marketplaces emerge and bloom and to populate data coming in and to sell data coming out, right? Not only that, it's not just about data marketplaces. At the same time, as you'll see shortly, it will also incentivize a global data commons. We have data commons here and there for AI, things like OpenML and otherwise, but there's no direct incentives for those even to merge themselves, right? So we actually have silos of data commons. So Ocean's goal towards the objective function is maximizing the supply of relevant data, right? So this is sort of the objective function in words, right? Maximize the supply of relevant data. And then token rewards, Ocean tokens, if you supply data and curate it. And the curation part is actually really important because how do we know what's relevant, right? Can we hard code into the algorithm somehow what's relevant? Can I decide? Not really. We have to let the crowd decide, right? And what better way to let the crowd decide than let people put their money where their mouth is, right? This is the idea of curation. And we actually use something called a curation market. So to drill in on this, the economic incentive for Bitcoin is the following. Maximize the supply of relevant data, like I've talked about. So we are rewarding the curating of data and making it available, right? So if someone actually has a data set that they really believe in, then they can stake on it. They can put Ocean tokens saying, I really believe in this. And then when people ask them for it, they serve it up and make it available to them, right? And so the curating is the betting on the data, right? And the sooner you bet on it, the earlier you bet on it, the more that you'll make for that amount of tokens. So it's basically rewards the early tastemakers. So overall, you guys remember the objective function, the block rewards for Bitcoin. We had the expected reward. We had the hash rate. We had the tokens, right? Here, it's, once again, we have the expected reward, right? In this case, it's the expected reward for a given user for supplying a particular data set, right? And then we've got the heart of this, which actually binds two things. We've basically got the prediction of the popularity of the data and the actual popularity of the data, right? And then we've got the tokens that are put out during that interval, just like Bitcoin is 12.5, right? So let's drill in on these two things. So the predicted popularity, this is basically people saying, I think that this data set is going to be valuable, useful, relevant, popular, right? How? They're using a curation market. I'm not drilling into that today. It's something that my friend Simon Delouvier came up with about 9 months ago, and it's starting to get more widely deployed. So it's a key building block that's emerging in the space. Just like, you know, in car design, you have you know, internal combustion engines or radiators and so on. So in the world of blockchains, we're starting to see an emerging set of building blocks, including something called curation markets. So this is the predicted, and then we actually have the proofed popularity, right? So the proofed popularity is basically, it makes a count every time you serve that data set up, and you have to serve that data set up in a provable fashion. It could be, for example, in a proof of space-time setting, like Filecoin. That's actually a bit of overkill, but that works. Or you can use something a bit more lightweight, like a direct proof of availability, like the guys at TrueBit have done recently. And together, we call the predicted and the proofed popularity a proofed curation market, right? So this is kind of the new construction that we have in Ocean, proofed curation markets. And then basically these things bind together, and we have the tokens. So to summarize, Ocean is rewarding you if you bet on the future popularity of a data set, and then it actually is popular in a provable way, right? So, but this was data, and in fact, we started with data as we went down the path of Ocean, you know, many, many months ago now, right? But then we started to run into some challenges. And the challenges were that, hey, you know, we've got medical healthcare data, and we need some privacy-preserving compute on that, right? Or in some cases, data is really heavy, right? We've got, you know, a petabyte of data here, and we're not moving it. We need to actually compute on-premise. And also, there's actually a whole bunch of emerging decentralized ecosystem plays that are doing really great decentralized AI compute. You know, the likes of SingularityNet, or privacy-preserving compute like Enigma, right? Or even general-purpose compute like Golem, right? So how do we link those into the ecosystem? And what we realized is, what we can do is generalize Ocean ever so slightly to say, not just maximizing the supply of relevant data, but of relevant AI data and services. Services being the key word. So replace data with services, and then we are rewarding curating of services and proving that that service was delivered, right? So once again, we have the same formula as before, but now instead of just the predicted popularity of the data, it's actually of the service. And same thing here, the actual proofed popularity. And in this case, though, the proof popularity, instead of just being, you know, a proof of space-time or proof of data availability, it might be, say, a zero-knowledge proof for compute, right? or some other privacy preserving compute, multi-party computation, all this sort of thing. All of these plug into here. And these things will be going into Ocean. There's actually this emerging field as we speak. It's starting to really explode in the last couple of years, especially within academia, basically developing more and more of these proofs. And this is basically what Ocean is going to be serving. So you can actually frame this overall that Ocean is a network of curated services, right? Or an AI services pipeline. For example, if I'm trying to train a deep net, right? I've got a bunch of input training data. The first thing I need to do is clean that up. So I run it through some outlier detector, some other simple algorithms, clean it up. So I've got my initial set, I've got my clean set, and in between I've got an algorithm for cleaning it up, right? Then the next thing I would do is run TensorFlow or some other training algorithm, maybe on a big Tesla cluster or something. I would build that neural network, and then I would actually end up with the weights for that neural network as its new data set, right? And then finally, I would simulate that and output the simulation of it, right? Every single one of those, the sort of data, compute, data, compute, data, compute, right? Ocean is actually the connective tissue among all of those. This is what we're going for. So here, what I'm showing is examples of projects, other projects in the space that could be plugging in. I'm not implying partnership or integration with these right now. This is just to show an example to the community about what's out there. So for production, there's everything from data services in government. For availability, there's things like Filecoin, SIA, storage.io. There's discovery, things like search, and this leverages in the curation market. In consumption, we've got consumption from a data perspective, like our partner Dex in Singapore, as well as from the compute perspective. Everything from prediction markets of Augur and Gnosis to general compute like Golem to SingularityNet for AI type compute. Privacy preserving compute like NuCypher and Enigma. Interoperability, proofs for that can actually fit into this here too. Polkadot, Cosmos, TrueBit, Interledger. And finally, towards this Ocean Commons, right? So this is really our vision for Ocean overall, is an AI services pipeline, a decentralized AI ecosystem for compute and for data. Some examples of Ocean. Self-driving cars is really one of the places where we really started. And the idea there is, McKinsey calculated we need 500 billion miles worth of miles driven in order to have accurate enough self-driving cars. We already have the algorithms, right? They're pretty good. But we just need more data, a lot more data. And 500 billion miles is more than Toyota or Uber or anyone can really get on their own in the next year or 2 or 5. And you might say, well, just pool your data, guys. But these are big corporations, right? It's not like they're gonna sing Kumbaya and hug, right? So you need to incentivize them somehow to share. And the perfect way, of course, is with something like Ocean, which directly incentivizes that pooling of data, right? So we're iterating with companies on this, including Toyota, for basically self-driving cars. And it's a win-win for everyone. Fewer accidents, right? There are millions of lives lost every year in auto accidents due to human error. And that could really get reduced. And then even just more mobility, right? It's going to make it easier for other people to take a car. It's going to be cheaper and so on. And by the way, this is a prototype we built with Toyota Research last May for this and presented in consensus. Also, healthcare research. So a great example is cancer. It's well known that early detection of cancer makes all the difference to survivability rates, right? So if you can detect cancer at an earlier stage, then you have a way better chance of treating it. Once again, this is a data problem. The better the data, the better the model, the earlier the detection. So we have iterations there as well. And the idea there, of course, is instead of just data inside each individual hospital silo, imagine you can actually build models that uses the data inside each silo and at the same time as preserving the privacy of each of those silos' data. This is actually possible now, especially thanks to these new privacy preserving compute approaches. My favorite example is OpenMind, which uses something called homomorphic encryption, which actually literally computes on encrypted data. It's kind of amazing. And finally, eroding the data silos, right? So, we hope that as Ocean gets adopted, we start off here, but bit by bit, it erodes away, right? So, so I have a couple final slides on why it's super important to get this objective function right. So, there's this idea of something called the Paperclip Maximizer, invented by Nick Bostrom in 2003. He's sort of a philosopher, singularity guy. And he talks about, suppose we have an AI whose only goal is to make as many paperclips as possible. The AI will quickly realize that it would be much better if there are no humans, because humans might decide to switch it off, right? So the future that the AI would be trying to gear towards would be one in which there are a lot of paperclips but no humans, right? It's trying to maximize paperclips, right? That's just the rational thing for it to do, right? It doesn't really model humans, it doesn't have them, it's just maximizing paperclips. So we go from one Clippy to an explosion of Clippies, right? And this is a philosophical problem, but it's maybe a possibility. And we've seen other instances of this. You know, Second Life had actually its own gray goo problem about 10 years ago, interestingly. There's also this idea from Ralph Merkle of blockchains as life. And you know, Ralph Merkle actually invented the Merkle tree and other crypto algorithms in the 70s, went on to do world-leading work in nanotech, and in recent years has also spent time back in blockchain land. And basically, I'll just give a couple quotes here. Briefly, Bitcoin is the first example of a new form of life. It lives and breathes on the internet. It lives because it can pay people to keep it alive. It lives because it performs a useful service that people will pay it to perform, right? It's incentivizing them. It lives because anyone, anywhere can run a copy of its code. It lives because all the running copies are talking to each other. It can't be changed. It can't be argued with. It can't be tampered with. It can't be corrupted. It can't be stopped. It can't even be interrupted. If nuclear war destroyed half our planet, Bitcoin would continue to live, uncorrupted. And interestingly, anyone who wants to create their own new digital life can do so, like Bitcoin. It will live on the internet, basically their own blockchain, right? So blockchains as life. And Ralph Merkle is a deeply respected cryptographer and scientist, right? And it is kind of interesting to think about, you know, blockchains, public blockchains, and DAOs as life forms, right? And even, you know, I've talked to people at complexity science institutes like SFI, and they don't see it as a stretch. You know, definition of life is basically shades of gray, right? Synthetic life, people have argued about this. So it's really not a stretch to call blockchains life. So remember this Bitcoin maximizing security thing, right? Well, it's basically maximizing energy usage, right? At an exponentially growing rate. And at the rate that it's growing, by mid-next year, Bitcoin will use more energy than all of USA. All of USA, right? It is a life form optimizing like crazy, just like this paperclip machine, but not for paperclips, but for energy of our planet. And you think energy is important? Well, you know, it's the thing we fight wars over. It's the thing that basically is maybe the most precious thing we have, right? So we have this life form out there, call it rogue, call it benevolent, whatever, but it is eating the energy of the planet. How is that for the power of incentives? So to wrap up, I've talked initially about blockchains as trust machines, right? But then I've talked about the superpower that blockchains have, which is blockchains as incentive machines. You can get people to do stuff. I've given the case study of Bitcoin. Then I've actually talked about a token design practice, right? About how to really think about token design using ideas from the optimization field and more. And then I've given a case study of Ocean Protocol, how we're using some of these ideas to help us to design Ocean. And finally, I have underscored how important it is to get this objective function right. It really matters. Thank you very much. All right, I see a question back there.
Hey, thank you very much. So you say that blockchains can make people do stuff basically by printing tokens. And how does this extend to the case where new tokens are not being printed anymore because you've hit the end of inflation? Now people have to still incentivize each other because there's only so much token in the economy. So does it still work, this argument that blockchain makes people do stuff?
Yeah, that's a really great question, actually. And there's two answers. One of them is, you know, the main one is we really don't know. There's a solution to that, and that is just have steady inflation every year. Like Dogecoin has actually 100% inflation per year, which is hilarious. But guess what? It's working, right? Bitcoin, we're actually already running into this issue, right? Because, you know, more than 75% of Bitcoins have come out. You know, we're seeing transaction fees of $100 versus, you know, 5 years ago it was like 0.1 cents. So we don't know. Now maybe Bitcoin is rolling along well enough, and it's, you know, it's deployed well enough that it has that momentum, and it no longer needs to print money to get people to do what it wants because it's kind of already got what it wants, right? And maybe that's good because maybe then it will stop paying people to eat, you know, the heat death, you know, turn the to suck up the life of the planet Earth, right? So maybe that's a good thing. But that's a great question. If we have diminishing block rewards, we really don't know. And even Bitcoin itself, you know, maybe we will see a hard fork where it will turn into an inflation-based setup, right? And other people have argued for the inflation-based setup too, most notably Albert Wenger. It really affects the economics and the value of the tokens in the early on days. Yep.
Thank you. I have one more question.
Yeah.
You're giving out tokens, and that's not really incentivizing per se, because those tokens don't have a value in itself, but you can do something with those tokens, and that's why they have a value. So that's what really makes it an incentive. In the case of Ocean and in general, how do you go about figuring out what the token should be able to do?
Yeah. So I see two parts of the question. The question of like, how tokens might have value or not, and then what is sort of the value embedded in Ocean, right? So money itself is the ultimate network effect. It's simply a shared belief in the value of that token, right? So the US dollar was backed by gold until the early 70s. Nixon took it off, and guess what? The economy rocked along even more than ever, right? So there was this shared belief, and some people might argue that, well, it's backed by the military, et cetera. But even if you took that away, you still have value. So basically, as long as it's there's some people believing there's value, then there's value. So it's more of a psychological thing at the very, very core than anything else, whether it's actually backed by anything, right? We do see examples of trying to be backed directly by stuff, things like the stable coins where they're backed by collateral in some way, et cetera, right? And it's easier to do. It's easier to value something if you are backed. So the simplest emerging blockchain out there that's very directly easy to compute is Filecoin. So in the case of Filecoin, and a lot of these other ones, people are using this classic method of evaluating an economy, right? And Ricardo from Ocean talked about this a couple meetups ago. So it's following this equation, PV equals MQ. So the M and the Q is the value of 1 gigabyte of storage for, say, 1 year. And then how many gigabytes of storage do you have? So that's basically the GDP, or the size of the economy. And then the PV side is basically the price of the token, and then the velocity of it, how many times is it being used. And then you just solve for the P. So P equals MV over Q, right? And that gives you the price of the token. So that's a sort of a classical economic way of approaching it. In this case, the fundamental intrinsic value for Filecoin is the hard drive storage, right? So in the case of Ocean, there's kind of two ways to think about it. One of them is simply there's the data marketplace side. So you've got this velocity for basically buying and selling data, right? But let's say for fun, we didn't have any data marketplaces and it was only the data commons. Then what's the remaining value? And that's actually in the staking of the data, in the basically the belief of the data over time. And Vitalik talks about this as a data sink, as a value sink, as a way of retaining the data. And basically it's people putting their money in where their mouth is for their actual belief in the value. So it is actually sort of monetizing this idea of belief, this shared belief in a token, right? So that would be basically how Ocean does it.
Got it. Thanks a lot. I'd love to talk to you afterwards because I have a very tricky token optimization problem myself.
Great. Awesome.
Thanks.
Thank you.
How do you ensure that data format are consistent and that people can actually read every kind of data formats?
We don't. This is the thing, right? Just no one will curate on it, right? If someone uploads garbage, then no one will bet on it and it will just sit there and it won't be used, right? So this is the wonderful thing, right? Or what if it is consistent, but it's just not useful for anything, right? So we're leaving that to the crowd. And so curation markets actually address a lot of these problems very naturally. Yeah. But it's a great question. Initially, we didn't have curation markets in the design, and we were trying to approach this in sort of more algorithmically deterministic ways. They all failed. So we really pushed it to the crowd, and it feels like it's going to work.
Can we call your startup Udemy for machines?
I missed that. Can we call our startup?
Udemy, the learning platform for machines.
You could call it that. I mean, overall, it's kind of interesting to think. I talked about how blockchains are ways to get people to do stuff, but you could actually replace the word people with people and AIs, right? Like overall, it might be that 10 years from now, 99% of the actors in the ecosystem are AIs running around as agents, right? So, and that's actually a good thing, right? Like overall, it doesn't have to be about this, oh my God, the machines are taking over. There's a healthy way to think about it, and I really credit JP Dormick for pointing this out to me. Think of it like Nature 1.0 is sort of, wind and earth and fire and trees is sort of this cradle for humanity, right? But imagine if we actually have a Nature 2.0 which builds on that with steel and silicon and adds more things to basically help support humanity in new ways with self-driving cars running around, self-owning cars, all of this, and they're basically helping us. And overall, I think that might be a very positive way to move forward with humanity. I don't know. Who knows where this will end? I'm optimistic, and I'm trying to steer all my efforts towards the optimistic side of things, but tries to raise the awareness, right? Because if we're not careful, if we come up with a bunch of terrible objective functions, we will optimize ourselves into oblivion, right?
Well, that's kind of what we do with data. Like we came up to the conclusion that more data is more knowledge, and more computing power and is more and better. That's like you said with cancer, like the earlier detection is the key, but it's not. Like it's a wrong objective function right there.
Well, we can debate about whether we want to detect cancer early or not, but let's offline that.
Yeah, so I'm thinking of protein folding at home and, the SETI at home. So people volunteering their computer to do useful calculations, not just calculate hashes which are useless.
Yeah.
So could you use something like Ocean to curate for people to bid on useful calculations and proof of work of doing something useful rather than proof of a hash function? Yeah,
definitely. And Ocean itself, like we're not emphasizing the heavy compute stuff ourselves. We really want to tie into the networks that are doing the heavy compute. So, and if you look around, like the literature of people like Golem or SingularityNet, this is exactly what they talk about, this useful compute, right? So, we iterate with these sorts of folks, and we really, with Ocean, they're getting Ocean tokens to participate in our network as well, right? But that's exactly it. So, Bitcoin is sucking up a lot of energy to solve, its objective function, but Ocean is actually much more lightweight that way and really leverage useful proof of work, both from a data store availability perspective as well as the compute perspective. Yeah.
Yeah. Thank you.
Yeah. Question here.
How would the introduction of quantum computing affect the security that is in Bitcoin and blockchain in general? Yeah.
So overall, great question. Quantum computing. How does it affect things? So my most recent information on this is from an expert a few weeks ago in a conference. In 10 years, there's a 10% chance that quantum will be mainstream enough to crack crypto. And in 15 years, there's a 50% chance. So that means, in 10 years, we could be in real trouble, right? And as soon as quantum went mainstream, it would basically, bust all the blockchains out there, right? There's a couple that are quantum tolerant. However, the quantum tolerant with very young quantum tolerant algorithms. And we know from the history of crypto that the young algorithms generally get broken, right? Like the early RSA algorithms and stuff from 20 years ago, 30 years ago, they were all very flawed, and those flaws were found very quickly. So we not only need to get better quantum tolerant algorithms, we need to figure out how to harden them as quickly as we can, right? So my view is that as it starts to get more and more probable that this comes along, then there will be hard forks from different blockchains to quantum tolerant algorithms, right? And there are some blockchains out there that are already quantum tolerant. It's just like very, very early days. So I'm not terribly worried in the sense of, given that a lot of people are thinking about this and worried about it, then I see simply that, for example, Ocean, it'll just be a hard fork when the time comes. Yeah. But you can't ignore it, right? There's another related thing, and that is there's now and then I see people doing medical data startups where they're actually literally putting the medical data on the blockchain, right? And and they're encrypting it. And they're like, oh, it's okay, it's encrypted, right? But what's happening is there's almost certainly out there smart hackers taking this data, downloading it, right? And they're going to wait 10 years, and then they'll get their hands on a quantum computer, and then they'll decrypt it, and then they'll blackmail the people for their medical data, right? So anyone out there, if you're doing a medical data startup, please, please do not put it on the blockchain. Put it, in storage behind a firewall, and use something like Ocean for access control, right? That's the right way to do it. Thank you. No, it just irks me like crazy, so, yeah.
Hi. In a blockchain system where the particular token that the system provides is not interesting for the people, what kind of different incentives do you think of that you can provide to humans? Right.
So so your question was the tokens that the system provides are not interesting to people, right? Well, in the case of Ocean, Ocean is also the token used for the data marketplaces. So people are actually using this as the currency to buy and sell data, right? So for data marketplaces, it's a currency, so it's directly useful in that fashion, right? Also, it could be within that closed networks on its own, But we'll probably see emergence on crypto exchanges, et cetera, who knows, right? But that's not really the goal of Ocean. The goal of Ocean is actually to be useful within the context of Ocean, right? If people want to convert it to other things, they can. But it's certainly useful even within its own framework.
This might be a very basic question about decentralized prediction markets, but how do you make sure that the curation system doesn't mess with the actual use of data? Because like when people stake a lot of tokens into certain data sets, other people might see that and they like might access, you know, it might be a self-fulfilling prophecy.
Yeah, so I mean, if there could be basically, you know, people that, let's say you've got a data set, it's getting curated, someone puts a big stake into it, other people are like, oh, that's cool, it must be cool, so other people start piling in. And maybe that first person, you know, they wait for it and they kind of, you know, run up the price and then they dump it, right? So pump and dump schemes, right? Just like we're seeing in this. So we have a few ways to counter this. First of all, I didn't emphasize it, but in the objective function for Ocean, the benefit you get for a given data set is actually the log of it. And what this does is, this is actually avoiding the stake whales. So if I have 10x more data, I only get 2x more benefit on that one, right? And what that does is it encourages diversity across lots of data sets, right? The other thing is in the bonding curves for the curation market, which is basically the relation from how much you're paying in Ocean tokens to buy this derivative token for the sort of stake in that data set, and you can have hysteresis, which means maybe you buy it for you know 10 drops of this data set stake, like. You buy the stake for X, but then if you sell it right away, you only get 70% of X. So basically, you're losing money if you sell it right away, right? There's a few other things too, reverse Dutch auctions, there's other approaches. And the cool thing is, there is actually an emerging community around curation markets, and people are talking about this, of different shapes that bonding curves can have and different things you can do to avoid these pump and dump schemes, right? And that's exciting, right? So we're really trying to leverage, you know, the best thinking on the planet around this. Yeah, question here, yeah? Or, sorry. I should. Yeah.
I'm not sure I understand how you will store all the amounts of data on the blockchain. Are you gonna use some kind of pointers? And how will you leverage your work at BigchainDB for that?
Yeah, so overall, Ocean is not storing any of the data on the blockchain, right? It has pointers, and the data itself can be stored in a decentralized cloud system, like Filecoin or Swarm, right, which has very straightforward proofs for that. It could be a centralized system, like say Amazon S3, centralized cloud, or it could be behind a firewall, right? And it's really important, like I mentioned, to get some stuff behind firewalls, things like medical data, right? And by the way, similar thing for compute, right? So you can have compute actually, you know, locally. You can have it on network, you can have it client side. So basically there's different places where you can mix and match where the compute is and where the data is. And then Ocean is basically about incentives and access control to basically connect the dots, right? And then your second question of, you know, where is BigchainDB playing a role? Right now we're in the exploration phase. Obviously we know the BigchainDB technology very, very well. We're not constraining ourselves to have to use BigchainDB. We see obviously that it has very good scale, it has access control features, all of this. So it remains to be seen, right?
So the data that will be stored on the like the centralized servers, like you said, will they be encrypted, or if not,
it's up to you.
Okay.
Yeah. I mean, basically, in each of these places, you know, whether it's Filecoin, S3, or on-premise, it can be encrypted or decrypted, right? It's up to you and making it available and so on, right? Yeah.
Thank you.
So Trent, back to the mechanism design,
yeah.
Because we're looking into it for the new stuff we're doing. The tricky part is governance, I guess. So you base your mechanism design based on certain assumptions, and even if we had the modeling tools that we don't have yet, we will need some kind of governance beyond code, let's say. What are your thoughts on that, and how you're trying to model it for Ocean?
Right, so that's a great question, Sherman. Governance, right? And I mean, you and I and many of us have had conversations about governance over the years. And you know, if you had have asked me 2 years ago about, say, like Bitcoin governance, I would have been just like totally poo-pooing it and whatnot. I think a learning that I've had in the last 2 years is that hard forks are actually working much better than anyone expected, right? So that's actually something. It's actually a tool. You know, Ethereum has a big community, but they've actually successfully navigated through the Metropolis hard fork, for example. Got some big features in there and so on. So, so that's sort of one way to view it, which means that we could actually have fairly simple governance if we just said hard forks for now, because we could actually hard fork ourselves into fancier governance. And that's kind of our current thinking right now. We actually explored a lot of like on-chain governance approaches, where you have everything from work from Tezos to Dash and so on. And some of those are working okay. Actually, Dash has actually gone through 20, 30 feature changes with its on-chain governance, and it's looking to be relatively successful. Who knows how it will go in the future, but that's a nice good example. BitShares, the early BitShares had some failures, so we'll see, right? But right now we're making it where Ocean is not dependent on any sort of governance solution, and when a best-in-class solution emerges, where it's worth the complexity hit, then we will adopt it. And there's other guys too thinking about this a lot, Aragon, Civic, these sorts of guys, right? Sorry, Aragon and Colony, yeah.
So you're saying governance by hard code?
To start with, yes, but we're very sympathetic to the on-chain governance protocols. It's just for simplicity, the first cut won't have that. But maybe by the time we deploy the production net, it will be on-chain, we'll see, right?
So we will have the last question now, and then we will have a break for 10 minutes.
Thank you. So you mentioned getting the objective function right really matters, right? That's very straightforward. However, in the traditional optimization problem solving, we do care a lot about the constraint of the all sorts, right? So how do you introduce like constraints and can be put also in the objective function or not?
Yeah,
like
so
energy use with this Bitcoin, right? Those kind of
that's a great point, actually, right? And so overall, there's a couple of philosophies around constraints. One of them is where if you run an optimizer and it comes up with something and you don't like it, then you add more constraints and then you run it again, and you add more constraints and run it again, right? And sometimes you can, after a couple iterations like that, you're okay, right? But sometimes you find yourself in what I call whack-a-mole, where you add something and some other problem pops up, and you add something and another problem pops up, and you just keep playing whack-a-mole for like a year. That's how I spent the first year of my PhD, was whack-a-mole on constraints. So there's a whole other way to think about it rather than trying to add constraints iteratively, and that is to come up with a really natural objective function that kind of goes a little bit higher level, that tries to capture the essence of it, right? That's hard. So in terms of constraints here, there are ways you can add constraints in, sometimes by simply having constraints built into the code, like hard things, sometimes by things like staking, right, which are sort of soft constraints, if you will. And it remains to be determined. There is no best practice of types of ways you can add constraints. There's sort of emerging practices around staking, and that's probably the best we have. Another thing that we do see, though, is fortunately, if we have governance even by hard forks, it means we can actually, at least in the early days, give ourselves flexibility to maybe change the objective function if we see problems, right? And maybe, there will be an old community that's like, no matter what, wants to keep that old objective function, fine, right? So maybe there will be a true fork like Ethereum and Ethereum Classic. We'll see, right? But it's certainly not a solved problem, right? I think one of the things I want to emphasize in this talk, I laid out to you some thinking here, but it's really early days in this, right? We are, it's a really immature field, this field of incentive engineering, right? And, let's develop it together. Thank you.